Yeah, in my last class I had discussed the operation of a dual converter. There are two single phase fully controlled bridges are connected back to back. So therefore, the polarities of both voltage and current can reverse. So if I use a dual converter to control a DC motor, all 4 quadrant operation is possible. In 2 quadrant, the machine is working like a motor. The difference is the direction of rotation is opposite. In the first quadrant, if it is running in the clockwise direction, in the third quadrant is running in the anti-clockwise direction, and during regenerative braking it goes either to quadrant 2 or quadrant 4. Another important application of a dual converter I will discuss sometime later after doing 3-phase bridge. There is a very important application. Okay. There are 2 types of operations. One is a circulating current type, another one is a non-circulating current type. In the circulating current type, both the bridges are triggered simultaneously. If alpha 1 is the trigger angle for bridge 1, the bridge 2 is triggered at pi minus alpha 1. Mind you, this condition we have derived assuming the DC link inductor is an ideal one. There is no internal resistance in the inductor, remember. Okay. Things do change if there is a finite resistance in the inductor. Okay. The second point that we discussed was the effect of source inductance. When the source inductance is 0, the moment the incoming thyristor is turned on, the outgoing thyristor turns off. Whereas due to the source inductance, for a finite duration both thyristors conduct. Therefore, during this period voltage applied to the load is 0 in a single phase. So I will repeat, during the commutation overlap period wherein both the thyristors are conducting, incoming as well as outgoing, the voltage applied to the load is 0. So therefore, there is a net reduction in the voltage applied to the load. The expression for the average value of the output voltage for finite mu is given by this equation, Vm by pi into cos alpha plus cos alpha plus mu, and here is the equivalent circuit. This is the average value of the output voltage drop due to the source inductance, the load voltage V0, and here there are 2 thyristors because in a single phase bridge 2 devices are conducting at a time, and we found that V0 is 0 for mu is equal to pi. It is possible only if the load is a ideal current source. Okay, and it is also 0 for mu is equal to pi minus 2 alpha, and we found that this is the case when load is an ideal inductor. Okay. Now value of I0 is given by this equation. Okay, Vm by omega L into cos alpha minus cos alpha plus mu. These expressions we derived yesterday. Okay. Now let me solve a problem in commutation overlap. A very simple problem, very interesting problem also. A single phase bridge, a finite source inductance, the load. Problem says that load current is constant at 10 amperes. Initially alpha is 0 and afterwards alpha is increased to 45 degrees. Determine the overlap angle, that is mu, as well as voltage drop due to the commutation overlap. Input voltage is the same, source inductance is the same, load current is just the same, except alpha is changed. Initially it is 0, now it is changed to 45 degrees. What happens? Remember, all parameters, input voltage, source inductance, load current, magnitude of load current is constant. So in this expression we will see that all parameters are constant, therefore cos alpha minus cos alpha plus mu is I naught omega L divided by Vm. So for alpha is equal to 0, 1 minus cos 30 is equal to, now alpha is 45 degrees, cos 45 minus cos 40 minus mu 1. Okay. Because it is said that for alpha is equal to 0, overlap angle is 30 degrees. When alpha is 0, overlap angle is found to be 30 degrees. Okay. So alpha is 0, cos 0 plus 30 is this, 45 degrees, 45 plus mu 1. So if you solve this equation, you will find that mu 1 is 10 degrees. So therefore, don't assume that just because Vm is held constant, load source inductance is same, and even if I keep load current is constant, mu, the overlap angle, will remain constant. No, it depends on alpha. A very important point to be noted. Okay. See, it is when alpha is equal to 0, when it is triggered at 0, commutation overlap angle is 30 degrees. Now when it is triggered at 45, it reduces to 10 degrees. 10 degrees. Okay. Now voltage drop due to source inductance at alpha is equal to 45 degrees, you just substitute here, is found to be 14 volts. It's quite substantial. Again, we are this is only due to source inductance. Now if I add say 2 volts each, so total voltage drop due to load inductance as well as the voltage drop due to the devices, it comes to around 18 volts. Okay. Yeah. More on dual converter, more on effect of source inductance we will see after doing a 3-phase circuits. So far we have studied half wave rectification. I told you that half wave rectification is used only for small power applications because the source supplies a finite DC current. Average value of the source current is finite in half wave rectification. Then we discussed half controlled bridge, which is also known as one quadrant converter, a fully controlled bridge, also known as two quadrant converter. Then we connected two fully controlled bridge back to back and we called it as dual converter, wherein all 4 quadrant operation is possible. I think our machine, in our machine course, our teacher might have told in low power application fractional HP motors are used, FHP motors in low power application. For example, fan is again fed from a single phase supply, single phase motor. So as the power rating increases, the trend is to go towards a 3-phase motor. So same thing is true even in power conversion. For low power application, you use single phase bridge. As the power rating increases, you go for a 3-phase. So we will study first 3-phase half wave rectification. Okay. So all the single phase bridges, there are 2 pulses per cycle. They are also known as 2-pulse converter, and we will find that in 3-phase half wave rectification there are 3 pulses, hence the name 3-pulse converter. So again, things are a bit difficult, please you need to understand, because so far there was only single phase voltage VI and Vm sin omega t. Now there are 3 voltages which are displaced by 120 degrees, magnitude may be the same. So here is the bridge. Okay, the 3 diodes, first we will do uncontrolled. They form a common cathode configuration, and load is connected between the common cathode and the start point. 3 diodes D1, D2, D3, they form a common cathode configuration. Therefore, the diode whose anode potential is highest will starts conducting. Okay. So here is the 3-phase sinusoidal voltages. Mind you, now you need to learn to draw a 3-phase sinusoid. Now you need to draw a clean 3-phase sinusoid voltages. Okay, they are very important. If you make a mistake there, it is going to be difficult to draw the output voltage waveform. Okay, so first exercise should be drawing a good and neat 3-phase sinusoid. Okay, so here there are 3 sinusoids. At point X, you will find that phase A becomes more positive than phase C. Okay, so this is phase C, this is phase A, and this is phase B. So phase A becomes, C cuts 0 and becomes positive. After 120 degrees phase B becomes, and after 120 degrees phase C. So this is phase C. So at point X, phase C, instantaneous value of phase C voltage is same as the instantaneous value of phase A voltage, and beyond point X, phase A becomes more positive. Similarly at Y plus, phase B becomes more positive than phase A, and similarly at Z, phase C becomes more positive than phase B. So common cathode configuration. So diode whose anode potential is highest will start conducting. So changeover from one device to another device will takes place at X or Y or at Z. Okay. So the diode which is connected to phase C will turn off at this instant at X, and diode connected to phase A will start conducting at X plus. Similarly at Y plus, the diode which is connected to phase B starts conducting, and the diode which is connected to phase A turns off. Similarly at Z, the diode which is connected to phase C starts conducting, and that connected to phase B turns off. So you will find that this duration, the duration for which each device conducts is 120 degrees. So I will tell you, this is 0, this intersection is 30 degrees, this is 60, this is 90, this is 120, this is 150, this is 180. So remember, there is an intersection at every 30 degrees. 30 degrees, 60, 90, 120, 150, 180. So similarly in the negative half. Okay. So diode starts conducting from 30 degrees to 150 degrees. So diode conducts between 30 and 150. So duration is 2 pi by 3 radians. Okay. So when the diode is conducting, the load voltage is same as the phase voltage. So if when D1 is conducting, load voltage is same as VAN, potential, this potential is same as this VAN, okay. When D2 is conducting, load potential is VBN, and when D3 is conducting, load potential is VCN, okay. So VAN, VBN, VCN. As I said earlier, there are 3 pulses per cycle, hence the name 3-pulse converter. I will assume constant load current of magnitude I0. So load current is constant and ripple free, and I will assume source inductance is 0. So changeover from one device to another device takes place instantaneously. So each device conducts for 120 degrees. Okay, the magnitude is same as that of the load current. So phase A supplies power from pi by 6 radians to 5 pi by 6, and it is 0. So if I find the average value of this, it is finite. So source supplies a DC component of current to the load. The effect I have already discussed in the single phase. Okay. Now, how do I draw the voltage across the when the diode is not conducting? Okay. In a single phase case, it was straightforward. Okay. In the 3-phase case, it is not very straightforward. Try to understand. When the diode is on, find voltage across it is 0. All of us know. And when the diode is off, you will see here cathode potential is the supply phase voltage, sorry, the anode potential is its phase voltage, whereas cathode potential depends on the conducting diode, because for some time the cathode potential is VBN, and for some time the cathode potential of D1 is VCN. So voltage across the diode for some time for 120 degrees is VAN minus VBN, and for remaining 120 degrees it is VAN minus VCN. Okay. So how does the waveform look like? At point X, so X minus, C was conducting. The diode which is connected to phase C, that is D3, is conducting. Okay. So voltage across diode D1 is VAN minus VCN. Okay. So if I take magnitude of each wave sinusoid is 1, that is 1 per unit. So at omega t is equal to 0, phase A is 0, but then phase C is 120 degrees. The instantaneous value is sine 120, that is nothing but root 3 by 2. Okay. So say here is that sine is VCN is proportional to sine 120 is root 3 by 2 per unit. VAN is 0, therefore VAK is minus root 3 by 2. Okay. So I have shown it here. At this instant, voltage across the diode connected to phase A is root 3 by 2 minus, it is blocking. Okay. Now what happens is, beyond the zero crossing, potential of A is increasing, whereas potential of phase A, that is VAN, is increasing, whereas VCN is decreasing. And at X both are same. Instantaneous value of VAN is same as instantaneous value of C phase. So VAK is 0. VAK is 0. At that instant, diode starts conducting. It takes, sorry, if I consider ideal diode, because beyond point X, phase A becomes positive. A positive voltage starts appearing across the diode, so it starts conducting. So this is it. So from 0 to 30 degrees, this is the variation. So from pi by 6 to 5 pi by 6, voltage is 0. Now how does the waveform look beyond 5 pi by 6? Beyond 5 pi by 6, diode which is connected to phase B starts conducting. Now it is going to be VAN minus VBN is the voltage appearing across the diode. Okay, same procedure. Okay, at this instant, that is at omega t is equal to pi, instantaneous value of VAN is 0, whereas instantaneous value of phase B is proportional to sine 60. Okay, this is 60. I will repeat, say 0, 30, 60, 90, 120, 150, 180. Okay, so this is, so instantaneous value of phase B is proportional to sine 60, that is root 3 by 2. So VAN is 0, so voltage across the diode D1 is VIN minus VBN is minus root 3 by 2. Okay. So what happens at pi plus pi by 6? That is somewhere at this instant. Instantaneous value of sine phase A is now sine 210. Okay, sine 210. This is 210, and whereas this is sine 90, sine 90, sine 90. So sine 210 minus sine 90. Okay, so sine 210 is nothing but minus half, sine 90 is 1, so minus 1.5, minus 1.5. Okay, so see here, at pi it is root 3 by 2, at pi plus pi by 6, that's corresponding to this instant, it is minus 1.5 per unit, minus 1.5 per unit. What happens after 30 degrees, that is 240, that is at this instant. At this instant, instantaneous value of VAN is proportional to sine 240. This is sine 240. Remember, you have to start for a phase A, this is the zero crossing. So this value is sine 240, whereas for phase B it is sine 120, sine 120. Okay, this is sine 120, and for phase A it is sine 240. Okay, what is that value comes out to be? Okay, sine 240 is minus root 3 by 2, and sine 120 is root 3 by 2. If I add both of them, voltage across the diode comes to minus root 3 per unit, root 3 per unit. See, I have shown you here, this is root 3 per unit. Okay, now what happens beyond 30 degrees? That is at 270, this is 270 now, or 270 minus, okay, because at 270 plus D3 starts conducting. Okay, at 270 minus D2 is conducting. Okay, so at that instant VAN is again 270, that is approximately 1. B is sine 150 minus, this is for phase B, this is 150 minus, so value is value is, see, 270 is approximately -1, Bn is half, so voltage is at -3/2, okay, because at pi plus pi by 2 plus D3 starts conducting. The moment D3 starts conducting, the voltage is now Vin minus Vcn. So prior to this instant, phase V was conducting, the voltage is Vin minus Vbn. So I have drawn it here. At this instant, pi plus pi by 2 minus, it is actually minus 1.5 per unit, okay. So remember, resistance is not very straightforward to draw, not very difficult either. So what you need to do is, you need to find out the instantaneous value of each phase value, okay. At this instant for phase A and phase B, you add them up, you will get it. So voltage across the peak value of the diode, peak value of the voltage appearing across the diode is √3 per unit. If it is Vm is 100, this comes out to be √3 into 100 is of the order of 172 volts or so. So at pi plus pi by 2 plus Vcn takes over, sorry, D3 takes over. Now voltage is Vin minus Vcn. You use the same procedure, the procedure which we used to draw the voltage waveform across the diode when D2 was conducting, and you will get the same waveform, okay. So what conclusions that we can draw now? Conclusions are, each diode conducts for 120 degrees, peak value of the voltage appearing across the diode is √3 times the peak value of the phase voltage, or √3 times the √3 per unit, okay. And if I assume load current to be constant and ripple free, RMS value is I0 into I0 by √3, okay. Now how do I determine the average value of the output voltage? There are 3 pulses in one cycle, and each pulse, the duration of each pulse is 120 degrees. So phase A starts conducting at pi by 6 and it stops conducting at 5 pi by 6. Output voltage is Vm sin omega t, okay. So average value is found to be 3√3 by 2 pi into Vm, where Vm is the peak value of the phase voltage, okay. So that is about half wave uncontrolled bridge. Changeover from one device to another device takes place at x, y and z. At point x and point y and point z, instantaneous value of two phases is the same. Since changeover from one diode to another diode takes place at these points, they are known as point of natural commutation. Remember, in a single phase case, single phase uncontrolled bridge, changeover takes place at the positive zero crossing for one and D1 and D2, and changeover from D1 to D2 to D3 to D4, it takes place at the negative zero crossing. So positive zero crossing and the negative zero crossing, they can be known as the point of natural commutation, whereas in a three-phase circuit, changeover from one device to another device takes place at point X or Y or Z. So these points are known as point of natural commutation. Therefore alpha, the trigger angle alpha for SCR is measured with respect to point of natural commutation. Remember, not with respect to the positive zero crossing of phase A, no, it is a point of natural commutation. Alpha is measured with respect to the point of natural commutation. Okay. The principle of operation of this bridge, a half wave controlled bridge, is same as that of an uncontrolled bridge. The only difference is the outgoing thyristor continues to conduct till the incoming thyristor is triggered. Okay. T1 continues to conduct till T2 is triggered. In this bridge, T1 continues to conduct till T2 is triggered. Okay. If there are diodes, it takes over, changeover takes place at X, Y, or Z. The only difference is T1 continues to conduct till T2 is triggered. Okay. So therefore, there is going to be an instantaneous change or jump in the output voltage, because when T1 is conducting, output voltage was VIN. Okay. When T2 is conducting, output voltage jumps to VBN. So it all depends on alpha. It all depends on alpha. That's all. So the average value of the output voltage, the expression is same as that of the half wave uncontrolled bridge. The only term that will come is cos alpha. That's all. Rest all remaining the same. Each device conducts for 120 degrees. Okay. Now let me draw the output voltage waveform. Let's see how does it look like. I trigger T1, T2, T3 at alpha is equal to 30 degrees. Okay. So where is alpha is equal to 30 degrees? Because any angle with this integral multiple of 30 degrees, I can determine on this waveform, because I said at every 30 degrees either it will cut the x-axis or there is going to be a intersection, because this is alpha is equal to 0, that is the point of natural commutation. Mind you, at this point it is instantaneous value of A is proportional to sine 30. Okay, this is proportional to sine 30, but alpha is 0 at this point. If I trigger T1, the corresponding value of alpha is 0. So 30 is here. So I'll trigger T1 at 30 degrees. The point of natural commutation or a point of reference point for T2 is Y. So this is 30. So T2 is triggered at this point. Similarly, T3 is triggered at this point. Okay. Reference point for the diode which is connected or SCR connected to phase B is Y. The reference point for the thyristor connected to phase C is Z. Alpha is 30 degrees. Prior to triggering T1, prior to conduct T1, in uncontrolled bridge, the diode which was connected to phase C was conducting. Remember, phase C was conducting. So if diode which is connected to phase C was conducting prior to T1 or prior to the diode D1, in a three-phase off-controlled bridge, prior to triggering the thyristor which is connected to phase A, the thyristor which was connected to phase C was conducting. Remember, so prior to triggering T1, T3 was conducting. So in this region, T3 was conducting. It continues to conduct beyond X because we have not triggered T1. So till you trigger T1, T3 continues to conduct. Remember, till you trigger T1, T3 continues to conduct. Till you trigger T2, T1 continues to conduct. So instantaneous value or load voltage is VCN. See, VCN, this is VCN at alpha is equal to 30 degrees plus T1 is triggered. Instantaneously output voltage jumps to the value proportional to VIN. So this is the value VIN. So it will jump to VIN and it will continue in this fashion for 120 degrees, provided the current is continuous. Remember, provided current is continuous. So T1 conducts from this instant till you trigger T2. At this instant T2 is triggered, instantaneous value of VIN becomes 0, that is why it touches the x axis. Immediately T2 is triggered. At that point instantaneous value of phase B is sin 60. Remember, see, this is 0 for phase B, 30, 60. So instantaneously it will jump to root 3 by 2 per unit. Root 3 per unit follows phase B again. At this instant, instantaneous value of phase B becomes 0. T3 is triggered. Output voltage jumps to VCN and follows VCN, and the cycle continues. So each device conducts, even in this case, for 120 degrees, provided current is continuous. Mind you, if I were to increase alpha greater than 60 degrees, greater than 30 degrees, what would happen? See, for a phase A, alpha is 60 degrees somewhere here, 30, 60. So prior to triggering T1, T3 was conducting. So output voltage is VCN, and you will find that VCN becomes 0 beyond this point. Beyond this point VCN becomes 0. At alpha is equal to 30, it just becomes 0. Beyond 30 degrees it becomes negative. So if I had a load which is purely resistive, current cannot flow beyond this point. So thyristor turn off of its own, because current has become 0. Current has become 0, and till you triggered the next thyristor, load voltage is 0, because none of the thyristors are conducting. So we would have had a finite 0 period if the load is purely resistive and alpha greater than 30 degrees. Remember, so if the load is purely resistive, current is just continuous. Remember, current is just continuous for alpha is equal to 30 degrees. Beyond 30 degrees, current will become discontinuous, because beyond 30 the instantaneous value of the outgoing phase goes negative, and you cannot have a situation wherein voltage across the resistor becoming negative in a AC to DC power conversion. Okay. Now I am not going to draw the voltage across the blocking thyristor. Procedure is the same. Okay. The only difference is, now you can have a positive voltage across a blocking thyristor. You just cannot have a positive voltage across a diode, because it is an uncontrolled device. Okay. Whereas you can have a positive voltage appearing across the thyristor. Okay. So I will just tell you, I will encourage you people to go back to your room and draw the voltage waveform across the blocking thyristor. See, at point X, instantaneous value of VAN is same as VCN. So voltage across the thyristor is 0. Okay. Beyond X, VCN is less than VAN. Okay. So voltage across the thyristor is VAN minus VCN. Okay. And VAN is, magnitude of VAN is higher than VCN. So therefore a positive voltage appears across VAN. It's possible, fine, till you trigger a gate of T1, it's blocking. Okay. So only difference is you can have a positive voltage appearing across a blocking thyristor. So beyond X, till you trigger T1, a positive voltage appears across it. The variation is the same procedure, VIN minus VCN. Okay. again 3-phase half wave rectification has a DC component. In the single phase case, from half wave rectification we went to full wave rectification. Same thing we will do in a 3-phase full 3-phase circuits. Remember, it is going to be a bit more difficult now. Here is the bridge. T1, T3, T5 form a common cathode configuration. T4, T6, T2 form a common anode configuration. Okay. VIN, VBN and VCN are the input voltages. As of now I will assume zero source inductance, no source inductance, load current is constant and ripple free. Okay. Whenever the conducting thyristor in the upper half, the load voltage is same as that of the conducting phase. In the lower half, potential of Y is same as the potential of the conducting phase. Okay. Common anode configuration, diode or device whose anode potential is least will start conducting or can be triggered. Similarly, common cathode configuration, diode whose anode potential is maximum will start conducting. I will repeat. In a common anode configuration or in the lower half of the bridge, changeover takes place at P, Q and at this point maybe R. Okay. So if I have an uncontrolled bridge, all six elements are diodes. At the upper half, changeover from one diode to another diode takes place at X, Y and Z, whereas in the lower half it takes place at P, Q and R. They do not take place at the same time. Remember, they do not take place at the same time. So things are a bit difficult now. Okay. Prior to triggering T1, T5, the device which is connected to C phase is conducting. Remember, when I had D1, D2, D3, prior to D1, D3 which is connected to C phase was conducting. Now please remember, I have changed the number suffix. I am calling 135462 because there is a particular reason. It will become very obvious as we proceed as we go along. Okay. So prior to T1, T5 was conducting. Similarly, in the lower half, if you see here, see this is the C phase, this is C and this is B. Okay. So diode which is connected to phase C starts conducting at P plus. Okay. And prior to C phase, B phase diode should conduct. Okay. So what is the number? So prior to C phase, the diode which is connected to B phase is conducting. In other words, 6 was conducting prior to 2. Okay. See, 2 is connected to C, 6 is connected to B. 6 is connected to B. Okay. So remember, B6 is, see here B phase is more negative. So 6, 2 and this is for phase A. This is for phase A. You will find that number is 4. This is for phase A. Whereas this is for phase again A, upper half 1. This is for phase B. We have numbered it as 3. And this is for phase C. We have numbered it as 5. Okay. So this point is same as this. Okay. I will draw the output voltage waveform for alpha is equal to 0. Alpha is equal to 0 is same as an uncontrolled bridge. Let us see how does the waveform look like. Okay. At this instant point x, T1 is triggered. At point P plus or at point P, T2 is triggered. The diode or device which is connected to phase C, that is 2 is triggered. Okay. At Y, device which is connected to B phase in the upper half is triggered, that is T3. And at point Q, see phase A becoming more negative, phase A becoming more negative. So the device which is connected to phase A, lower half, that is 4 is triggered. So you will find that, see, this is a sequence 1, 2, 3, 4. 1, 2, 3, 4. So that's why I have numbered the upper half as 1, 3, 5, lower as 4, 6, 2. Now let's draw the output voltage waveform. Please try to understand now. I said alpha may be measured with respect to the point of natural commutation. While drawing the output voltage waveform, you need to find out the instantaneous value of the phase voltages measured from the positive zero crossing. Remember, alpha is measured with respect to the point of natural commutation. That's all, nothing else. So at alpha is equal to 0, what is the instantaneous value of phase A? It is proportional to sin 30. So in the upper half, T1 starts conducting at x plus. Instantaneous value of phase A at that point is sin 30. Remember, this is sin 30. Okay, this is sin 30. In the lower half, see, this is phase B. At this instant, phase C, a device which is connected to phase C is triggered. So phase B was conducting at in this beyond this. Sorry, before this point, prior to this point, phase or the device which is connected to phase B was conducting. Okay. So potential of bus Y is B, and potential of X is VAN. Okay. So the equivalent circuit is C, VAN, T1, X, load, Y, T6, BBN, the load. This is the equivalent circuit. Okay. So at alpha is equal to 30, at the instant when you have triggered the thyristor, it is sin 30 for phase A and sin 270 for phase B. See, this is 270, sin 270 phase B is at the negative peak, so that is a -1. So output voltage is VAN minus VBN, you will find to be 1.5 per unit, 1.5 per unit. I am taking the magnitude to be 1. Okay. So at this instant it is 1.5 per unit. Okay. Now Let us see after 30 degrees what happens. At this point, okay, VAN is sin 60, VAN is sin 60 and VBN is sin 300, sin 300. So what is the value? What is the value? It is sin 60 is root 3 by 2, sin 300 is minus root 3 by 2. The load voltage is VIN minus VBN. It is root 3 times the peak of the input voltage, or root 3 per unit. Okay. So if you see here, it is root 3. It was 1.5, that is at alpha is equal to 0 or omega t is equal to 30 degrees with respect to the positive 0 crossing of phase here. After 30 degrees, the peak value of the output voltage becomes 1.73 times. Now let us see what happens after 30 degrees, in the sense just prior to triggering T2. See, at this instant T2 is triggered. What is the output voltage just prior to triggering T2? Still output voltage is VAN and VBN. Immediately after P, or at P plus, output voltage is VIN minus VCN. Till P minus, output voltage is VIN minus VBN. So just prior to P, VIN is at the peak. It's approximately sin 89 or so. Okay, that is approximately equal to 1. Whereas phase B is 330 minus, that is again half, minus half. So VIN is 1, VBN is minus half. So output voltage is VIN minus VBN, it is again 1.5. So during this instant, T1 and T6 were conducting. At this instant, T2 is triggered. Now voltage is VAN minus VCN. It continues for another 60 degrees. This is 60 degrees, mind you. See, this is 30, this period is 30 degrees, and here is again 30 degrees. So in this instant, T1 and T2 are conducting. Procedure is the same. To determine this output voltage. See, here is it. This is the procedure. VAN. Now we need to consider, okay, T2. Okay, mind you, this is to be now. You will find that if I assume the current to be constant and ripple free at IL, T1 conducts from this point till you trigger T3 at Y. So this is 120 degree duration. So T1 conducts for 120 degree duration, same as half wave rectification, 3-phase half wave rectification. Similarly, we have a common anode configuration, 3 devices forming a common anode configuration, again fed from ABC system. Now each device in the lower half also conducts for 120 degrees. So T force takes over at this point, mind you, T force takes over at this point, alpha is equal to 0. So this is the point of natural commutation. For the lower devices, so in this period T4 conducts, direction of current is now reverse, just opposite to that of T1, okay, and it continues for 120 degrees. So what observations can we make now? Each device conducts for 120 degrees, but then each phase conducts power for 240 degrees, okay. Each phase conducts power for 240 degrees. You just see each phase conducts for 240 degrees. 120 here, 120 there. At any given time, only two devices are conducting. At any given time, two devices are conducting. Just see here, T1 and T6. T6 is connected to phase B, T1 is connected to phase A. Phase C is open. In other words, phase C does not supply power in this period. At any given time, only two phases are on, third phase is open. Third phase is open. Okay. How many pulses are there in one cycle? There are totally 6 pulses in one cycle. I have just drawn 2 pulses, and we found that each pulse is of 60 degree duration. Each pulse is of 60 degree duration. Remember, there are 6 pulses per cycle, and each pulse is of 60 degree duration. Each device conducts for 120 degrees. Each phase supplies power for 240 degrees. See here, T6 T1, T1 T2. Now see, there is a sequence now, T6 T1, T1 T2, and in this region you will find that it is T2 T3, T2 T3, because T2 is conducting, T3 gets triggered here, is T2 T3, and from here T3 T4. That is why we have numbered as 1, 3, 5 in the upper half and 4, 6, 2 in the lower half. Yeah, more we will see in the next class. Thank you.